Hi, we are beginning a new adventure of number theory and we'll be discussing so-called quadratic residues. Now, I hope the last word will be meaningful for you and not be perceived as an offensive word. The first subsection is written right here. My another hope is that you're capable of reading what we are expecting to do today. Anyway, let's start with the definition. So suppose we have an, those are integers, and this n is going to be positive. We say that a number a is said to be a quadratic residue modulo n if the following equation has a solution. This one, x squared is congruent to a modulo n. If this equation does not have a solution, then we say that a is a quadratic non-residue modulo n otherwise. It has something similar to those blue equations you've solved so many times at school. For example, x squared equals 4 has a solution because you can take square root of 4 and you will generate two solutions plus or minus 2. On the other hand, x squared equals -1 does not have any solutions because how the hell can I take square root of -1 when we live in the real world? So intuitively to say a is going to be a quadratic residue if we can find, roughly speaking, a square root of a modulo n. Maybe I should write somewhere here. But this is just a rough intuition. Now here's a quick note. 0 in fact is a quadratic residue modulo any n. Well, for the obvious reason, indeed. If you consider x squared congruent to 0 modulo n, well, it has a solution, clearly x equals 0. However, for the sake of simplicity of constructing theory and for the sake of saving my nerves, we're gonna ignore this residue 0 throughout this section. Please keep this in mind. Also, I noticed from some authors they prefer to add a condition to our definition of quadratic residue that GCD of an must be equal to 1. So in other words, those numbers an has to be coprime. In my opinion, it's not super important for us, but we will see later where this condition is going to be important for us. Now here's a quick example. Let's try to find all quadratic residues modulo 7. Well, because we live in the world of modulo 7, we have only 7 possible so-called bad boy numbers. Those are 0, 1, 2, 3, 4, 5, and 6. But we've thrown 0 in the trash as we agreed before, so we have only those numbers from 1 to 6. Now let's just square each number here and see what we get in the world of modulo 7. There you go. So we have here 1 squared, which is congruent to 1 modulo 7, 2 squared is congruent to 4, 3 squared, it's equal to 9, but in the world of modulo 7, it's just 2. 4 squared is 16, in the world of mod 7 it's 2, 5 squared in the world of mod 7 is 4, and 6 squared is 1 modulo 7. Now those equations, they all imply that in the same world of modulo 7 we have a solution for the equation x squared is congruent to 1 modulo 7, x squared is congruent to 2 modulo 7, and x squared is congruent to 4 modulo 7. Well, here the reason is because you can here plug x equals 1 and you get this equation, and you can plug x equals 6 and you get the following equation. So in fact, this equation implies that 1 is a quadratic residue modulo 7. The same argument applies to number 2 and number 4 as well, so 2, 4 are quadratic residues modulo 7 as well. Now the last 3 numbers that weren't mentioned before, and I mean 3, 5, 6, those aren't quadratic residues, so quadratic non-residues modulo 7. Now notice that we are in the perfect world modulo 7. Perfect just because 7 is a prime number. And in this specific case, you probably see that we have 3 quadratic residues and 3 quadratic non-residues. So we have equal amount of residues and non-residues as well. Now here's a general proposition for the following note. So you suppose that you have an odd prime number p, then there are exactly p minus 1/2 quadratic residues modulo p, and the same amount p minus 1/2 quadratic non-residues modulo p. So for our specific case, if p an odd prime number, which is 7 here, then we have 7 minus 1/2, which is just 3 quadratic residues modulo 7 and 3 quadratic non-residues modulo 7, as we had before right over here. Now I really feel bad for throwing out another prime number, which is 2, so let me just discuss quickly what will happen here. If your prime is 2, then there's only one quadratic residue modulo 2, and that is number 1. Well, we also have 0, but we've thrown him out, as you remember. The first step of the proof is gonna considering the following set, so we just numerate all numbers, different numbers modulo p, 1, 2, p minus 1. Remember, we do not include 0 right over here. But instead of this set, we can actually consider the following set, which are also different elements modulo p. So we have minus p minus 1/2, minus p minus 1/2 plus 1, then it goes to -1, then we skip 0, we have 1, then all the way up to p minus 1/2 minus 1, and then p minus 1/2. Maybe it seems counterintuitive what I've done, so let me just give a quick maybe example for some partial case. So let's suppose, for instance, you have prime number equals 7, so you have those different elements modulo 7. So this one represents the first set right over here. But we decided to write in another way. So what I did, I just took the second half of the set, 4, 5, 6, and substituted 2 other elements which are congruent modulo 7. So 4 I substituted to -3, 5 is substituted to -2, and 6 is substituted to -1. So instead of typing 4, 5, 6, I could have typed here -3, -2, and -1 right over here. This -3 represents just minus p minus 1/2, -2 is minus p minus 1/2 plus 1, and finally this one is -1. I hope it makes sense right now to you. Now if I square all elements from this set, we get the following. We have 1 squared, then 2 squared, and then the last one p minus 1/2 squared. -1 squared is just 1 squared, this one is just p minus 1/2 minus 1 squared, and this one is just p minus 1/2 squared. So squaring those sets, we just get rid of the half of the elements. Well, just because if we go back to our partial case where we have 1, 2, 3, minus 2, minus 2, minus 1, and we square all elements, we get just 1 squared, 2 squared, 3 squares. So we just divide the total number of elements by 2. My main claim here is to show that this set forms a so-called residue system modulo p. So in other words, those elements, 1 squared, 2 squared, p minus 1/2 squared, are all completely different in the world of modulo p. We're gonna prove this claim by contradiction. We actually gonna suppose that there are 2 different elements such that those squares are going to be congruent modulo p. So we take x, y from 1 to p minus 1 over 2, and we claim that those are equal modulo p. So then we can rewrite this as x squared minus y squared is congruent to 0 modulo p, and by definition of modulo, it means that this prime number p divides x squared minus y squared, which is which is just the same as saying x minus y times x plus y. And now since p is a prime, this breaks down into 2 possibilities. So the first case here is when p divides x minus y, so it means immediately that x minus y should be congruent to 0 modulo p, and thus it means that x is congruent to y modulo p. However, we said that we take two different elements xy such that those squareds are congruent, and we got that xy are the same, which is not possible. I think I should have been more explicit. Let me just to explain in detail. So we had x minus y is congruent to 0 modulo p, but furthermore we have the following inequalities. X and y, they are between 1 and p minus 1 over 2. Those two inequalities, they imply that x minus y should be less than or equal to p minus 1 over 2 minus 1 and bigger than or equal to the same number with minus sign. Now you should notice that this number is strictly less than p, whereas this one is strictly bigger than negative p. So x minus y squeezed strictly between negative p and p. Now x minus y congruent to 0 modulo p means x minus y can be equal to 0, p, 2p, 3p, or negative p, and so on and so forth. And the only possibility left here, according to this inequality, is when x minus y equals 0, and thus x equals y, which is a contradiction to our assumption because we took different x and y from the beginning. The second case is a bit trickier, but still doable, especially for you guys. So p divides x plus y is the last possible option that we have. However, let's recall that x is between 1 and p minus 1 halves and y is between 1 and p minus 1 halves. Now if we add those inequalities, we get x plus y, which is squeezed between number 2 and p minus 1. So it's squeezed between two numbers that aren't divisible by p. P divides x plus y means x plus y might be equal to either 0 or p or 2p, 3p, or even negative p, negative 2p, and so on and so forth. And we see that x plus y, according to this inequality, cannot be neither p, nor 2p, nor 0, nor minus p, and so on and so forth. So something is wrong right here. So we reached to the contradiction to our assumption that this is not a residue system modulo p. So contradiction means that actually this system is a residue system modulo p. Now see, here we have p minus 1 half elements, different elements modulo p. But we know that each of those elements, so 1 squared, can be congruent to some number a1, and this a1 is between, well, we exclude 0, so not 0, between 1 and p minus 1. Then 2 squared is congruent to another number, different one, because those elements are different, because this is a residue system. So 2 squared is congruent to some a2, and so on. P minus 1 halves squared is congruent to some other number a, maybe p minus 1 halves. Those a's are elements from 1 to p minus 1. Some elements. So thus, these equations, they imply that we have p minus 1 halves quadratic residues, modulo p. And the rest p minus 1 halves elements that didn't get into those, they are quadratic non-residues modulo p, and that's what we needed to show in our proposition. Now I just would like to leave 2 exercises to make some gains in your brain. So first of all, I would like you to find all quadratic residues modulo 11 and also find all quadratic residues modulo 9. So the difference between 2 exercises is that in the first one I give you a prime number 11, whereas on the first case this is not a prime, this is a compose. And when you find all quadratic residues modulo 9, modulo composite, try to compare the results with the proven proposition above. So I mean, you should convince yourself that maybe for composite numbers the proposition does not hold.